Hi, my name is Daryus Chandra, and I work for Photonics, a quantum startup company located in beautiful British Columbia, Canada. So, Photonic approach for quantum computers is using spin-based qubits in a silicon with a photonic interlink. For my physicist folks here, we are using T-Center. I'm working for Photonic as quantum error correction researcher, also known as experimentalist biggest enemy. So, so here I will tell you something about our recent publication about QLTPC codes. The title is Computing Efficiently in QLTPC Codes. You can find it in archive, but in this presentation, I will not tell you the details, the mathematical details about it, because you can put it in Google, you can read it on your own pleasure. But here I want to tell you what are the lessons that we learned during the development of this quantum error correction codes. So since the conception of information theory by Claude Shannon in 1948, the design of error correction code always try to find the delicate balance between the code word length, the number of information bits, and the minimum distance, which dictates the error correction capability of your codes. So traditionally, we have the same approach for designing quantum codes. So we will try the early study of quantum codes. We will look at this balance. What is the number of physical qubits? What is the number of logical qubits? And what is the minimum distance? So that's fine, but now as we try to scale up, try to look at the bigger, the longer term, try to reach the utility scale of quantum computer, that trade-off is not enough. So here, this is the QEC code, the Quantum Error Correction Codes Design Handbook. So we should, in the future, when designing quantum error correction code, should pay attention to just beyond, pay attention beyond the encoding rate. Encoding rate is great because it tells us the ratio between between the number of physical qubits to logical qubits. It making commercially relevant quantum application more practically feasible because it tells you what is the size of your quantum computers. But also at the same time, not all quantum codes can be implemented in the hardware. Different platforms give you different constraints. It gives you different advantages that you should also consider during designing your QEC codes. And the third aspect is if you have a good codes like in sense of, oh yeah, the encoding rate is great, the next question will be, can I implement the logical gates? Can I do logical operation with my newly found codes efficiently? Because, okay, if my encoding rate is great, it's much better than surface codes. Now, the problem is if you cannot do logic efficiently with your codes, then whatever the overhead advantage on your quantum error correction codes, if you cannot compile it efficiently, it will be swallowed by your overhead of doing logic. So basically, the current approach, the state-of-the-art approach of implementing logic with QLTPC codes is using lattice surgery. And we know that lattice surgery requires D round, which is the minimum distance of the code. So basically, as your code gets better, you actually need more syndrome extraction rounds. So you actually impose more overhead if you just follow the state-of-the-art approach for doing logic in quantum LTPC codes. Yeah, and at the same time, you want good error suppression, which is manifest as good large good distance, fast syndrome extraction, low complexity, low latency, and accurate decoder. So I can have good codes, but it is useless if I cannot decode. It is if I have good code, it is useless if my code need maximum likelihood decoder, which is not good. It is not scalable. So in we at Photonic in fault tolerance team, we try to design our code with these four things in our mind. So let's see if we can satisfy these four requirements at the same time. So one, we try to leverage non-local connectivity that is natural to our platform in Photonic because we have this inherent capability of connecting non-local qubits using the Photonic link that inherent available in our qubits to use this family of codes called QLTPC codes, quantum low density parity check codes. So yeah, one, does it provide a better encoding rate? Yes. Does it fit your hardware requirement? Yes. So we have now like strikes two of the requirement that I've presented you before. So now let's take a look how we implement logic in the QLTPC codes that we just launched like a few months ago. So in this scenario, the way we implement logic is by interleaving logical operation, depth one circuit of logical operation with error correction cycle. And you repeat this depends on like what is the depth of the circuit that you want to run. In this example, it's a quantum circuit of depth 3. So it will be logical operation, error correction, logical operation, error correction, logical operation, error correction, and so on. So what is nice about this is an efficient logical operation allows us to implement sliding window decoder, low latency, high performance decoder. So one thing that like a lot of people doesn't really aware about quantum error correction codes is like we decode over, like look at this amazing animation. So if you look at the structure of the matrix that we need to decode over a quantum circuit, it exhibits something called like spatially coupled structure. Spatially coupled structure is like very prevalent in the classical error correction codes. So people already just like to bring back what Hermann Hauser said this morning, let's learn from classical error correction codes. So like if your matrix if my circuit that performs logic have this structure, logical operation, error correction, logical operation, error correction, then my parity check matrix, the matrix that I need to decode over to perform error correction will exhibit spatially coupled structure. And this allows me to do something like this. So over time, what I do is I do error correction with window that move along the logical operation. Because one thing that you don't want in your quantum computer is you have engineered your qubits so good, so fast, but then you forgot about optimizing your decoder. Now the problem will be your decoder is your bottleneck. So yeah, think about the classical resource of your error correction. So so the third question in the QEC handbook, can we perform logic efficiently in QLTPC codes? The answer is yes. Because we can do logic efficiently this way by performing logical operation interleaved with error correction, which manifests like efficient in quantum, efficient in classical. So it's all good. So the question is like how we scale up. Like we agree that monolithic approach is probably not very feasible in the future. So a lot of codes will exhibit like multiple copies of like QLTPC codes networked together. So in our paper, you can see that we have tried this by implementing 2 code blocks of QLTPC codes that we refer to as like subsystem hypersimplex codes or SHIPS codes. So 2 code blocks of SHIPS codes. So this represents 18 logical qubits with 126. It's a depth 126 Clifford, and this is, I think this is like the most comprehensive, the most sophisticated circuit level noise simulation involving QLTPC codes with logic in it. So now just to conclude everything, when you meet a quantum error correction codes, so when you see a new quantum error correction codes being proposed, so feel free to ask this question. So, is the implementation of logical operations in your code efficient? Can they be decoded efficiently? How do they operate modularly? Because these questions are ultimately the ones that are more important beyond your encoding rate. And also, like probably the next aspect of it that I want to highlight is the classical computing resource for QEC codes should take more precedence. It's not like I'm not saying that it is the most important, but like it is very important to start thinking about it now. Because decoding this matrix, so the matrix that we need to decode for depth 126 has 10,000 rows and 500,000 columns. So that is the scale of like any classical decoding, classical error correction chips like never reached before. So yeah, that's all from me. Thank you so much.